How's it going, everybody? In this video we're going to break down the BGP best path selection algorithm, or for people like me that have to say that over and over and over again, the BPSA. The idea of the BPSA is to allow you to manipulate on a per route basis or per prefix basis, and when it comes to BGP path selection. Now, the cool thing about BGP is you can be very, very, very wide or very, very, very granular, depending on your individual needs. And I will give you an idea of how that would work and some of the different capabilities that are out there for you to manipulate the BGP path selection when it comes down to actually manipulating BGP. Because if you understand the algorithm that's working behind the scenes, and you understand how to which attributes to use to manipulate what type of traffic, and what type of circumstances you could use, then when you actually go to manipulate traffic, you'll know where to look, what to expect, and all that good stuff that goes along with it. And most importantly, you'll understand which way to place your path selection in. So you're going to be doing inbound, or you're doing outbound, and what is the desired result. So if you understand the outcome, then and what you have to do to get it there, the BPSA is actually very, very simple. It's just that you need to make sure you understand what exactly you're trying to accomplish. Now, the main thing that I want you to remember, though, is this is different than IGP best path selection. And the reason I say that is when it comes to IGP, you're not manipulating the route, you're manipulating the link. Because with IGP's path selection is influenced based off of, with RIP is the hop count, with OSPF it's the cost of the link that the traffic is going to be forwarded over, and EIGRP by default is going to be bandwidth and delay of the link. So if you go in and you manipulate that, if you manipulate the link attributes, so the bandwidth, the delay, or how many hops away something is from somebody else, that is going to be manipulating the link, and therefore any traffic that's got to go over that link to get to a particular destination is going to affect all routes, unless you were to go to the router and make a manipulation like policy-based routing, which we haven't covered yet in this series. I will be doing that later on, where you can manipulate where the traffic is coming from and where it will go to. So that's a source-based routing, where most IP routing is destination-based. So you take a look in the routing table, you see where the destination IP address is, and you say, okay, do I have a route in my routing table? If yes, then you forward it. You switch the packet to the outgoing interface, and then you forward it out to where it's got to go to the next hop. If you don't know where it goes, but you do have a default route, then you forward it to the default route, because you have a way of letting go. You have a shortest match, which is the default route, to handle something. If you happen to have a route that comes in and you don't know where the destination is or how to get to it, and there's no default route, you drop the packet, because at that point you don't know how to handle it. It's like you hit a dead-end road, and when you're looking at it, all you see is either a brick wall or you see an open green field. Maybe maybe you hit a dead end, or what they sometimes in the U.S. here they call it no outlet or dead end, which means the road doesn't go anywhere. So they haven't built onto it or what have you. So I mean, in the real world, you could probably drive over the grass if you know where you got to go, but in routing, it doesn't work that way. Once you get to the dead end, it's either you know what to do with it or you have to redirect it. So, which policy routing can do that as well. So you can say if it's coming in this direction, you can forward it out. You can forward it back out. Which, the funny thing about that is that's kind of how inter-VLAN routing works. If you think about it, you hit a router and you're going to be going back out the same way you came in. And which actually kind of goes against with the split horizon rule, but that kind of doesn't really apply in that regard. So we'll talk more about that in later down the road. Now the BPSA, if you understand the concept of the different attributes, that's going to be the main thing: is what attribute does what and why. Now there's a couple of things you have to understand about the BPSA before we can even get into the nuts and bolts of it because of the fact of what it does. So the prerequisites are pretty straightforward, but they need to be understood before you can handle any traffic. So basically, the first one is next hop. Next hop must be in the routing table, so it prevents route recursion failure. If you don't have a next hop value, or if you don't know how to recurse to the next hop, you won't be able to forward traffic. Now, basically, what that means is, if you need to get from point A to point B, and you don't know how to get there, then you're not going to be able. Then you can't go any further than that. There's technically 13 different potential matches that you can have. Weight, local preference, down to I believe the last one is lowest or highest IP address of next hop or something like that. I'd have to scroll down to the bottom because I have them all labeled here, and I'll go over them just so you guys understand them. But the idea is, if you don't know how to get to the next hop, so for instance, if you've been advertised a route, but you don't know how to get there, then you have to be able to you have to have a valid next hop that you can recurse to. Or what will end up happening is in the routing table, it'll show up as an asterisk, which will be a valid route, but the greater than sign will be missing, which is the best path. That best path, if you don't get any greater than signs, that's a bad day, because that's telling you don't know how to get to where you need to go. So we'll cover that, and I'll show you what that looks like. The general idea is, if you don't know how to get to somewhere, so for instance, like I've shown you several times in our environment, where when you peer via eBGP, when you peer that, the next hop value is changed. When you do via iBGP, the next hop is not changed. So, for instance, if you have an edge router that's connecting up to the internet, and you peer via eBGP with that router, so your next hop is going to be the IP address of the provider. So we'll say 10.1.1.1. Okay. Then you peer via iBGP. Down from, say, router 1 and router 2 are connected, and router 2 is the provider. He's got an IP address of 10.1.1.1. Router 1's got a... Actually, let me draw this out. I think it'll make it easier for you to follow along. So, in this case, we peer with this subnet right here. And when you peer via eBGP, you type in the neighbor command, you type in 135.0.0.0.1 here, and then this guy is .1, this guy is .2, right? So you peer, the adjacency comes up. Well, if you look at the routing table and you do a show IP BGP and you learn routes in here, the next hop is going to point to 135.0.0.0.1, right? Well, what ends up happening is, if you peer via router, when we peered up here on router 5 down to router 11 via iBGP, the next hop didn't change. It was still 135.0.0.1. Now, why is that? Well, that's because router 5 peered with router 13, and that was the IP address that was used in the neighbor statement for R5 to peer with R13. So that's how you would realize, that's how eBGP works. Your next hop is going to be the IP address you use in your next hop value. So whatever the neighbor command, whatever the neighbor IP address is you use in your neighbor statement to peer with that neighbor, that is going to be your next hop value. Now when R5 peers with R11, and it's an iBGP peering, R5 says, okay, well, this is the next hop I have, so I'm going to send it to you. R11 looks at the route and says, well, I don't know how to reach 135.0.0.1. And router 11 goes, it's a valid route because I'm getting it, but it's not a best route because of the fact that I don't know how to recurse to it. So on R5, this is where you'd have to either change the next hop to next hop self, type in, neighbor, whatever router 11's neighbor is. I forget what I typed in. We'll type in 115.0.0.2, for instance, and we typed in next hop self, which means router 5 would be the next hop to router 11. So then router 11 would know how to get to router 5, and then when the traffic would get to router 5 would know how to get to router 13, and therefore traffic would be okay. But when you're dealing with the next hop, if you can't recurse to it, then that's a bad sign. That's a bad day. You need to go in and fix that. Then we have the synchronization rule must be met or disabled. So this prevents legacy black hole issues that might come into place. Now, synchronization, I don't know if you're going to need to know this, and let me look that up real quick so that I give you the correct definition. Okay, so I went out to the BGP frequently asked questions, and I said, what is synchronization and how does it influence BGP routes installed in the routing table? The answer to this, if your AS passes traffic from another AS to a third AS, BGP should not advertise a route before all routers in the AS learn about that route via IGP. BGP waits until IGP propagates the route within the AS and then advertises it to external peers. A BGP router with synchronization enabled does not install IBGP learn routes into its routing table if it is not able to validate those routes in its IGP. Issue the no synchronization command under router BGP in order to disable synchronization. The idea here is if IGP doesn't know about it, you can't advertise it. So by disabling that, you doesn't have to know about it. You can go ahead and just advertise it via BGP. So I wanted to cover that before I got any farther. So the idea here is synchronization is disabled by default, so you don't even have to worry about that. Either it's met, which means IGP and BGP are both learn the route, or you just turn it off. An Aas path must not contain local AS. Remember eBGP loop prevention here? The idea here is similar to what we've already talked about with the allow ASN, which simply means that if I have AS1, I go over the global internet, and then I have another site that's got AS1, and I'm advertising a route out. If I learn my own autonomous system number in, I'm going to drop it because of the fact that I don't want to learn something in that I already know how to reach. Well, let's say, for instance, that spoke site doesn't already know about that route or isn't originating a route. You could simply go in and say, well, in that case, allow ASN would take care of that problem for me, so all I'd have to do is go in and say, I want to learn that route, allow ASN would disable the loop prevention mechanism, and then you'd be able to learn your routes in. And the only time you would do this is where I want to be very clear on this, the only time this is applicable is when you're dealing with IBGP peerings. This means that you're going to be peering to another site that is going to be the same autonomous system as you. Because this is the only time it affects it, is when you are advertising your own AS number. Now, the other type of issue that you might run into with down the road is it's kind of a corner case, but it is applicable, is when you're doing summarization or you're using the aggregate address. Because when you use the aggregate address, you're aggregating a bunch of routes into a shorter match. So you're able to, you're supernetting, if you will. So what ends up happening is you may or not realize that when you're supernetting, you might be your autonomous system might be in the Aas path, which would be a bad sign. That's a bad thing, because then you might be relearning routes in, and then you could get into a loop. They have they have a command that you can use in aggregation, which is ASSet, which basically what it does is it goes into the hidden AS information, the Aas path information. It's actually in the header. It's in the BGP updates. It's just that it's hidden because of the aggregation. It goes in there, pulls that information out, and it populates the Aas path field. So instead of you learning in a route that you advertised, your allow ASN is being disabled, of course. If you learned in a route in and you saw your own AS number in the update, you would drop the update because you originated that, and that is very possible for that to happen. I haven't actually seen it in production. I just know that the capability is there. So if you are summarizing and you're forwarding traffic out, and you happen to be transiting a couple other autonomous system numbers, and then through whatever means it happens, basically what ends up happening is if your autonomous system number is in that Aas path field and you advertise the route in that summary, you would learn it back in again. And that could cause potentially a loop, and you don't want that. So by using the ASSet command, you're able to, like I said, populate the Aas path field, and that's going to, when your autonomous system number sees its own autonomous system coming back in, it's going to drop the traffic. So it's going to prevent the loop. So the other thing too is the first autonomous system in the Aas path must be the neighbor's autonomous system. Now, the BGP enforce first AS command is used to enforce that. The idea behind it is the first AS number you should see should be your directly connected neighbor. If it is not, then you could have a problem, because then that could mean someone's spoofing something or something else might be going wrong. I've never actually even played with that, so I'm just going to make you aware that the first autonomous system in the path must be their neighbor's AS, which is the guy you're peering with directly. So let's take a look at the actual the order of the BPSA, and then we can go into and break down each one of them individually. And I'll explain how each one works. So when it comes to applying policies, the idea behind this is when you're applying your policy, you're going to say, route or local preference in or local preference out, things like that. That's actually a bad example because you would only say that inbound. But when you're applying a change outbound, you're modifying routes into the network. And if you're applying a change inbound, you're modifying routes as they leave the network. So just remember that. We'll come back and touch on this more in detail later. You have the pre-best path community. This is actually outside of our scope, so we're not even going to touch on that. That's a CCIE level topic, but we will not even touch on that. There's technically one in between these two. Can anybody guess what that one is? Actually, we just went over into quite a bit of detail just a few minutes ago. And since no one's on this video with me, I'll break it down for you. It's the recursion issue. Do you have a valid next hop? If you don't have a valid next hop, then you're not going to be able to even, it's not even going to be able to be manipulated through the BPSA. So the idea here is if you don't even have a valid next hop, then you can't run BPSA on it, so it's not even worth talking about. And then we have wait. Wait is the very first one. It is set inbound, and it's Cisco proprietary and locally significant. So the idea behind this one is if you can set the wait on a per link basis, so you can type in neighbor whatever and then wait and instead of wait, and then that's going to be set outbound. It's going to be set inbound. That's going to affect outbound traffic. Now, what if your device is handling traffic that's outside the network? Now, if you're handling traffic outside the network and you want to be able to use wait to influence it, you can't use wait for a locally originated route. It just doesn't work that way. You could have traffic that is going to be you learned in, and you want to determine how your network is going to reach that network, but it can't be something that's internal to your network. I've tried this and it doesn't work. So it's done inbound. This is for how routes will leave your network, and the reason why it won't work for routes that are internal to your network is because they're already internal to your network. You probably already have an IGP route to it, so there's no point of you trying to use wait to influence something back in. Remember, wait is to leave the network, not to come back in. And the higher value is preferred. So that's going to be one of the things you need to pay attention to. And I'm going to cover the first, let's see, 1, 2, 3, 4, 5, 6. I'll cover the first 6. I think that'll give you guys a good rundown. I've actually gone through all of them, so I know how all of them work. And I'll break down med when we get down to it. Then we have local preference. This is set inbound as well, and this is how traffic is going to leave your network. The idea here is a higher value is preferred. By default, there's a value of 100. So if you make the value of 101, that particular network, that particular link is going to be more preferred than others. Now they actually have, you can do this. Local preference is unique to the autonomous system, which means that it's local to the AS that you're working inside of, and when you set this, it actually propagates out to all of your neighbors in your autonomous system. And it is a way for you to, you can go in and set it inbound to affect outbound traffic, and if you want remember the higher value is preferred. So if you want to, you can go and set a lower value. So you could drop a local preference for a neighbor configuration down to 90, and that'll make it less preferred. And Now you can do this the default local preference, which means that for all routes it's going to be this particular value, or you can do it for a particular autonomous system. So I'll show you guys how to do an Aas Path access list, or it could be per prefix. You can do that as well. So I'll show you guys how to go pretty wide and granular, all with the same situation. Now we didn't talk about confederations. I'm probably going to do that as an add-on video, just because of the fact that it's not very widely used, but it's more of a service provider type of setup. Most places that I've worked at never touch it. They might use route reflection, but the idea with the confederation is you have one very, very large autonomous system, and you want to break that up into smaller sub-autonomous systems. Well, when you're dealing with sub-autonomous systems and you have two of them, and you want to exchange routes between them, they view each other as eBGP routes within inside the confederation. Now, local preference is passed through confederation eBGP peers, but not actual eBGP. Now, again, if you have no idea what I'm talking about, I will be covering this later on. I'll actually lab it up and show you guys how it works. It's actually pretty cool, and there's some unique identifiers when you get into it, but it's important to understand how that would work. But again, it's one of those things that's very, very lightly touched on, and even in my CCIE prep, we never even really got into it. I did it just so I could play with it, and I thought it was kind of cool. And there's a question: can you? Somebody just actually popped in on me. Can you use route reflection with confederations? Yes, you can, and that's like a very, very corner case scenario, but you can do that. Then we have locally originated routes. Locally originated routes mean you either use the network command, the neighbor statement, or I'm sorry, network command, redistribution, aggregation, or you did some sort of manipulation to get the route advertised in. And all those routes are advertised with a weight of 32768. And so it's like weight, but you aggregated it to the device, meaning you either advertise it into BGP somehow. And then there's not a whole lot you can do with that, as far as I'm aware. Once it's locally originated, that's pretty much it. Then we have the Aas Path. Aas Path is going to be like your trying to think of a good way to put this. Like in RIP with your hop count. So the shortest Aas Path is going to win, and it's going to be more preferred because it's probably closer. Or EIGRP feasibility condition. If your metric is lower than mine, you're the better route. So that's the general idea of how we would work with that. Now you can go in and if you want to with Aas Path, this is how traffic would come back into your network. So you could set this outbound, and this is going to affect inbound traffic. And the nice thing about this is when you're dealing with that, it's you could set a route map, and you could in the route map set the Aas Path, and you could prepend, what they call Aas Path prepending. And what basically the idea behind that is you're going to add your autonomous system number 2, 3, 4, 5 times into the actual Aas Path length, and then you advertise on a particular neighbor, and then that neighbor that you applied it to will be less preferred than another route into your network. So a friend of mine refers to it as prepend.as. It's a joke in most circles where you're going to prepend that autonomous system number, so which means you're going to make it less preferred in that route. And typically you would add 3 in the Aas number. So if, like, let's say your Aas is 200, so you would type in set Aas prepend to 200, 200, 200, and then the idea behind this is when you're doing that, you're gonna, let's say you've got five links. Let's say you got 4 links, and you have a main circuit that you want to use traffic on. Then you have a network or a link that you would want to be a second, one is third, and one is fourth. So on the second preferred link, you would use Aas Path prepending 3 times. So you do 200, 200, 200. For the third one, you would do 6 times, and then for the Fourth link, you do it 9 times. The idea here is you're putting enough Aas Path numbers into the Aas Path so that it does not realize what's going on. It does realize what's going on, but the routes back into the network are less preferred through these routes. And if the first link goes down, the second link will become the most preferred. If the second link goes down, then the third link will be the most preferred. And if the third link goes down, the fourth link will be the most preferred. Because of the fact that you're going based off Aas Path length, remember the shortest one wins. So if your shortest one is 25 Aas hops, then that's going to be your winner. Then we have origin, and it's IGP over EGP over incomplete, which means that you're going to choose an IGP, which is an I, and E, which you can't actually even do anymore. It's supposed to be a hidden command, but I have not been able to get it to work. EGP is actually the predecessor to BGP. BGP came out, I think, in 1994, and EGP was before that one. And even before that one, a little history lesson for you, was GGP, or Gateway to Gateway Protocol. This is back in the days of the ARPANET and when the Department of Defense was setting up the internet, back when everything was command line and the internet wasn't even really an internet back then. So the idea with the origin code is you're going to prefer IGP over incomplete, which IGP means that it's going to be the network command. The redistribute is going to use the question mark. So if you have a route that's being redistributed, but you have 2 equal cost routes, and all of the attributes match all the way down to origin, and you want to prefer a route, you can go to the origin and say, set this up so that it looks like it's an IGP, and then based on the origin code, the origin would be better with the IGP versus the question mark, so then it would choose the I over the question mark. That's the general idea of how that would work. Then we have the med. Now we talked about med previously in some other videos, but the med is just simply a metric, and a smaller value is preferred. It is only compare between peerings to the same provider by default. If you have multiple peerings to the same provider, this can help choose the exit. There are lots of exceptions, and I will cover that here momentarily. This is only for leaving the route, leaving the network. It's called the multi-exit discriminator for a reason. How do you want to leave your autonomous system number? Or how do you want to leave your AS? If you are going out and you want to leave the network via router 1, via router 2, or instead of via router 2, usually what you can do is you would set local preference. But let's say, for instance, that you don't normally use this, but it's important to remember how it's important to know how it works. That the general idea with med is that's going to be an upstream situation, meaning the provider is going to be trying to influence your routes outbound. So the idea here is and the only time this comes into play is if all these other attributes match, or they're equal, so that there's no tiebreaker is med. So weight matches, local preference matches, local origination matches, Aas Path matches, origin matches, med. This can be your tiebreaker. Remember, all these are tiebreakers essentially. So if you have this attribute, this attribute, this attribute, this attribute, this attrib, that attrib, they all match. You get to the next one down, and there's a difference. That's gonna be your tiebreaker, and you're gonna choose whichever one has the better, based off of the attribute specifics. So, for instance, if it's med, the lower value. So I'll show you guys how to do this as we go along, and I actually set this lab up to be able to go through all 6 of these. But typically, your provider is not going to do this. The provider is going to do local pref. The provider is going to do Aas Path. You're going to do Aas Path prepending. Remember, prepending is how you get back in the network. Med is how you leave. So you could say local pref outbound, inbound, and that's going to set how you're going to leave your network. But you could have a situation where it is set, and you would set the metric in a route map outbound to the provider, or to the customer, and then when you receive that, you're going to choose one way over the other. By default, it's 0. So anything, if you go a number higher than that, that's going to be less preferred. So the idea is you're going to set the med on the router that you want to choose. You're going to set med in. You're set med out on the router you don't want to have the customer come in on, because the lower metric is preferred. You wouldn't set med on the route or the incoming PE router that you want your customer traffic to come in on. And this way here you can affect how it goes. Now you can do this on like I said, you can do this on a for all traffic. You can do this for a particular AS number. You can do this for a particular subnet, and this will allow you to pick and choose which way traffic moves. And it's important to understand how this would work. So at the end of the day, it's relatively straightforward, but if you don't know how this stuff works, you can get yourself into trouble. So in this case, we've got everything situated out to this point. I don't really see a reason to go much farther beyond that. I think the top 6 is good enough. But let me talk about the different specifics when it comes to med. You have a few different capabilities with med to worry about. And the first one you're going to take a look at is going to be med is a non-transitive attribute, which means it should not leave your autonomous system. But you can set this outbound to a from the provider down to the customer to affect how the customer will route outbound towards the provider. That is definitely a possibility. Now, you have a couple of ways of doing this. You can do always compare med, and always compare med is going to allow you to take a look at the way that the traffic is forwarding. So the idea, sorry, I got distracted with a phone call. Always compare med is going to look at med regardless of what's going on. So if you use this, even if nothing, you have other options upstream, you're always going to take a look at always compare med. And this can be good or bad, but depending on the situation, you may want to choose one route over the other. But always compare med is going to help you out with that. Now the one below that, best path med confed, this is only applicable when you're dealing with confederations, and compares med for routes locally originated in the confederation. So I'm not even going to talk about that one because of the fact that we're not going to be, at least right now, we'll talk about confeds later on down the road, but that's more of a corner case scenario. The other thing that we want to take a look at is going to be missing is worst. And you might be thinking, okay, what does that mean? Well, when you receive med in, it's going to be coming in as a med of 0, right? So, and we can prove that. So let's actually take a look at a router and see what we have going on here. So let's take a look at router 5. We'll do a show IP BGP, right? We notice how all these routes here that are coming in have a med of 0. All these guys right here. Well, because they're coming as a null or no, 0 med, that's going to be an indication to us that we can use BGP missing is worst. Meaning if the med is missing, or 0, you can change it to 4.2 billion. So it's going to be, remember, the lower med is preferred. So if you have, if the med is 0, you switch it to 4.2 billion, then you're going to have a whole bunch of routes that are going to be, that if there's no med, they're going to be the worst routes. So that's going to be one way for you to, one tiebreaker. I've never actually seen this used. Just be cognizant that it's out there, its capabilities to be able to be used. The other one is going to be deterministic med. So you're going to compare med against all possible paths, because you might have a couple different ways to getting off the network, and you're going to want to take a look at them and to use it deterministically. This is sort of similar to always compare med, but there are some differences. And I'm not going to get too much deeper into that because of the fact that I think I'm going way off into the weeds of best path selection. But if you want to know more about that, I would definitely look those up and take a look at them. But as far as I'm concerned, that's way beyond anything we're going to touch in this in our series here. There was actually an email that I read the other night, and I do some contract work where I teach routing protocols on a per needed basis to small companies and stuff like that don't have the on-site staff to do it, or they want to learn more about it. So I'm actually looking at doing an all BGP series on a pretty large topology and explain how stuff works, and getting into doing an MPLS piece of it, and in addition to all the other capabilities you can use with BGP. Because BGP, people think just, well, it's internet routing. Well, there's a lot of stuff you can do with BGP beyond that, and the idea behind it would be to show you all of, from a grand scale with hundreds of routes, how that would come into play. Because if you understand how BGP works fundamentally from this level, then taking it to the next level of going into a deep dive and really looking in detail, looking at every aspect of the BGP algorithm, looking at lots of routes and different types of manipulation, and looking at MPLS and understanding fate sharing, and where fate sharing is, you're not going to have both your MPLS service and your internet service running over the same wire. So in case there was the wire was to break, you wouldn't lose the internet and MPLS service at the same time. We can take a look at doing a large-scale BGP clusters with route reflection, and do a big BGP med or confederation setup. So there's lots of little things that we haven't even covered yet that are available and out there that I've worked with in production, that if you chances are you won't see, but the possibility is still out there. It depends on who you work for, because if you work for a big service provider, BGP is their bread and butter. So you're going to have like Aas or OSPF as your IGP doing your like MPLS, and you're going to be doing BGP and probably a BGP free core. Where if you happen to have I work with one customer, a little bit larger of a customer, they had some pretty large BGP deployment. I'd say probably 25 or 30 routers running BGP, and we needed one router to do all the reflection. Well, they didn't want to go out and spend a ton of money on a box that's going to have, because they were going to be receiving 25 separate views of the BGP table, and they had full views of the table. So like 480, 500,000 routes. And I said, well, this is where we deployed a CSR 1000V in their ESXi environment, and this box we gave it 12 gigs of RAM, and away it went. I mean, it didn't even miss a beat. It took all the different views in, reflected out what it needed to. We were good to go. So that's one example of how that would work. But then there's a question: why 12 gigs of RAM? If you were to look at the breakdown, actually, let me pull up a router real quick, and I'll show you what I mean by that. If we were to do this and show IPBGP, let's see here. Is it in here? No, it's not. I'm sorry, show Bgp Summary. Now, if you look right here, I'm only learning I've got 52 prefixes. That's it. I'm not a very large BGP topology at all. And actually, this is pretty minuscule in most cases. The table version is 831. That means there's been 831 changes since I got this all spinning up. And there are 32 network entries using 4,600 bytes of memory. But that's with 32 routes. Just imagine if you had 500,000 routes. That could be a couple, that might be a 500 meg. And then if you do 25 of those views, 500,000 views, that's going to just start adding it up. There's actually, if you were to go, let me take a look at real quick. Let me pause the video. I'll pull up a BGP route server and show you guys how big of a BGP table that can be. Okay, so I pulled up a route server, and if we were to do a show route, this is a Juniper router, so forgive me here. I'm not exactly show route all. Or sorry, show BGP summary. Let me scroll this down just a little bit. Blow this all the way up. So, as you can see here, we have all these routes. Did I lose my connection to it? No. Alright, so what we have here is, this is the BGP table, and right now for IPv4, it knows about 535,397 routes. It has 0 suppressed, 0 in dampening, 0 pending. So as you can see, we have all these different paths. So we type in show route all, or actually let's do brief. So if you take a look, we have a static route here going to 12.0.11, and then we have 1.0.0.0/24. These are all the different ways we can get to where we need to go. The validation state is unknown, which means it was redistributed. And we can go through here and this, I mean, I'm just looking at where this stuff is coming from. Notice how it's 1.0.192.0/18. So right now, this particular route is the best because it's got the highlight. So now if I was to hit the Q and do a trace route to, and actually it's, because these are all summaries, it's very difficult so if I was to do a trace route to 1.0.192. We'll say 1. This is public internet. This is a public route server, and if you notice, it's being this is being MPLS routed. So this would be what you refer to as a what? Any ideas? This would be referred to as a if it was IPv6, it would be a 6 VPE. Or I'm sorry, 6PE, meaning it's basically going over the public internet. And the thing is, it hits this autonomous system number, so it hits 61.19.7.102, and this guy doesn't know what to do with it. Is basically what this is saying. I don't know what to do with it, so I'm just going to drop it. So we hit Control C to break out of that. So that's the general idea of how this would work. Remember, this is a Juniper route server, and as you can see, this is the BGP table. Right? A lot going on here. And so if we were to take a look and show route protocol BGP, and we'll say summary in there. Oh, it's the same thing. So show BGP summary. Yeah, see, it's not giving me what I was quite looking for. Let me look for another server real quick. That's AT&T. Let's see here. Let's look for... And actually, there's a question. How do you get to those? It's actually pretty simple. You bring over PuTTY. And then I would, let's see here, let's find Time Warner Telecom in Denver. So, copy the link address, pop this guy in here, pull this guy out, copy and paste this in, but pull the telnet out. And then go over here to 23. Pull this guy up. Now we're on this box, so we're going to type in rviews, RVIWES, and then it's going to be RVIWS 123. Another Juniper router. Okay. Actually, I don't want a Juniper router. I want a Cisco box. Let me see here. I'm in the US. So let's see. Hostnet. Copy link address. Let me close this guy out. Yes, I want to close that guy out. Pull up another one. And bring this guy over. And this one's going to be, password is routes. Bingo. Alright, now this is going to be a show ver. Pipe include iOS. Enable. That'd be crazy if I could. Okay. So basically, show IP route. Show route. Another Juniper box. Show route. What are my optional commands here? Show BGP summary. Show BGP summary. Show BGP neighbors. This is going to take forever. Okay, well, the idea that I was trying to show you is that when you're in this box and you're looking at, yes, I want to close that out. When you're looking at this, you're going to get the more routes you have, the larger the more memory you're going to take. So the idea here is to make sure you understand that if you've got, in this case, in our case here, we don't have that many neighbors, that many connections. But if you get, 60, 70,000 connections, and you have, well, let's say even 25. Let's say you have 25 different peers that you're connecting to. That's going to indicate that you have, and you're receiving 535,000 routes per neighbor. That means you're going to be having whatever 25 times 535,000 is. I don't even know what that is. Let's actually take a look at that calculator. We'll type in 25 times 535,000. That's going to be 13.3 million routes. And then you have to go through the best path BPSA on all these routes. And then you might have more than one best path. You could have 20 best paths, as we've seen. So that gives you an idea of the complexity of BGP. So that's where that comes into play. So again, when you're dealing with the best paths, the BPSA, if you want to affect routes into the network, you're going to set your changes outbound. If you want to apply routes as they leave your network, it's going to be inbound. We'll take a look at that more in detail later on in the next video. So I'm going to do an individual video per one. So wait, local pref, locally originated. I'm not going to even touch, but I'm going to do Aas Path, origin, and med. I'll show you guys how that would work. I hope this has been informative for you. I want to thank you for viewing.